Greetings, everybody. This is our lecture on memory design, and this is the one that is going to replace today's lecture at 12:30. In this video, we're going to talk about memory design, and some of these slides we went over in our Monday class, and so I'm going to record this particular video with a little bit of a repetition of some portions of this would be a repetition, rather, I should say, of what we did on Monday, but there'll be some new material towards the end. So, as we talked about this in our Monday class, when we think about memory design, we're thinking about something that is hierarchical, and we have things that are fairly fast but also expensive on the left hand side, such as scratch pads and register files. And as we go up in the other direction, we then see caches and primary memories, and then secondary memories, even tertiary memories, depending upon the kind of system we use. As I said, some of these things probably need to be revised. I should talk about if I could actually make any changes. It looks like this is an image, so I can't really change it. But if I were to be able to change it, I would make the figures a little bit more inflated here. So this would be more like in the terabytes range, and this would be more like several gigabytes, and this would also be something in the order of megabytes at this point in time. The register files are still not as big as, or the increase has not been as aggressive, except some of these solid state memories that are coming into market that may ultimately replace the entire register space of a CPU, but that remains to be seen. So the idea is to figure out how to make the computer or the CPU feel at ease as in fact addresses that are requested, or the operands or data that we request out of our hierarchical memory such as this, how this structure can be prevented from creating a latency between the CPU and then the rest of the structure. So that by that I mean the amount of time it takes to access an operand from the rest of the system outside of the register file is going to impact the performance of the CPU. So what we would like to do, ideally speaking, is to figure out a way that we could find things most of the time in what we call this cache, without having to do a lot of replacement or a lot of searching in the higher, the more back end of this memory structure here. So what comes to mind in this regard is what's called caching, which takes place between primary memory and cache as a way of bringing things in and out of cache. And this graphical representation also suggests that we got more primary memory, along with the numbers here, than a cache. So therefore, we're going to be able to we're going to have to work with a cache that's smaller than primary memory. But a lot of our information will come from primary memory, as you would remember from best move instruction. And so we need to find a way to minimize the amount of replacements that we have to make as we bring things in from primary memory to cache. This is called caching. If this procedure that I just referred to happens between the secondary memory and primary memory, then it is called paging. So paging is when things move from the secondary memory here to the primary memory, where the basic building blocks are pages that are held in these primary memories as consecutive locations. Whereas if that happens between the primary memory and cache, then we're talking about blocks, and then block frames, where blocks get hold. And I guess here we can still refer to page frame, and this would be like a cache frame. So a cache frame is something that that holds a block, and a page frame is something that holds a page. So now that we said that, let's take a look at maybe some of the technologies that are out there. So dynamic RAMs are those things that actually are volatile. That means that they lose their information and they have to be refreshed. They just have to, they're capacitive sort of loads, and they have to be recharged. and they are considered to be fairly fast otherwise, compared to the rest of the memories that we might have. Static RAMs are among the fastest, and they actually are also volatile because they will not hold their values unless the power is supplied, but you don't have to refresh them. And then the ROMs are, and the PROMs, and then the EPROMs, or double EPROMs. These are things that are static, and these are combinational circuits, and they're non-volatile, and they're used typically in BIOS chips and other situations like micro storage, I would say, containment, and they cannot be produced with the same volume as these other memory elements can be, but they're out there and they get used. And then we have the magnetic and optical serial access memories. They're serial in a sense that basically the way that we access information is not random. So in order to get to a place, you have to get to a place before that place. That's what makes them serial. And these typically are tapes and floppies and compact discs and hard drives. They're larger in size, but they're slower. And they're slowly being replaced by solid-state drives. But it's taking some time for this to happen because these still provide a lot more memory at a cost that is much cheaper than what a solid-state drive would require for the same amount of memory. So as maybe the technology advances, that these solid-state drives will ultimately replace some of these serial memories that have a lot of some, I should not say a lot, but some level of mechanical parts that may actually break down more so than a solid-state drive would. So the advantage is certainly tilting towards tilts towards solid-state drives in that regard, but the cost aspect of this latter technology here still prevents a wider use of these technologies, this particular sort of drives at this point in time. But that may change. So here's just maybe a graphical representation of a disk memory structure, which is a multi-platter structure. It's got 4 platters or cylinders, and then the sequentiality or the serial nature of this, the access is visible here. That you got to get onto a sector. Well, you got to get onto a cylinder or a platter, and then once you are on a platter, that means at this point in time the diskette has to move from, let's say, this platter to this platter, or from that one to this one. So that takes some time. And once you're over here, then you have to find a track. And once you're on the track, then you're finally more or less on your sector, and then the sector will be some number of pages that you can copy onto your primary memory. And like I said earlier, this would basically be some kind of a paging process. Now we're going to focus on caching here, because paging and caching are similar, as I said in class on Monday, except for perhaps some implementation details. The main concept remains the same. So let's take a look at this cache idea in the most elementary form that we could have it, and that's called direct memory map. The idea is, again, as I said on Monday, we take our blocks that are in our main memory, and in this example we're setting up a block of 32 words, and then we have 256 words in all, so we got 8 blocks here. And these blocks basically are assigned a fixed frame in what we call a cache. A frame is something that holds just a block, no more than a block, exactly a block. And so as you see in this diagram, block 0, for example, is assigned to frame 0. And so is block 4. They both go to frame 0. And block 0 goes nowhere else. And likewise, block 1 and 5, they go to frame 1. And whenever they are needed, that is, they're going to have to be coming into these frames. And only one frame is allocated to each block. And this is called direct memory map because you're just mapping. It's also called static assignment, each block to a unique frame. And as a result of which you don't have the flexibility if in fact frame 0 is occupied by a block 0 at the time that block 4 is needed by the CPU, it has to be kicked out of there. And if block 0 and block 4, again, as we talked about this in class, are the most frequently used blocks, then even though the other frames may not be as occupied and may be available, when block 0 is there, and if they're to kind of alternate, the requests go between block 0 and block 4, that would be a bad design, of course. Then you will have to be replacing block 0 by block 4, and then replacing block 4 by block 0, and that clearly adds to the latency of the computation, if you like. The CPU will have to wait for these replacements. The way you find out which block is in a frame is by way of a tag, which identifies the block that is actually in the frame. So when you come to access a block, and you know exactly, and you'll see this in just a little bit, what frame it actually is assigned to, and then you just search for the block ID. You could see that in this situation, we have a 1-bit block tag, which happens to be the leftmost address, and then a 2-bit frame address. So as you can see that if in fact we're in block 0 or block 4, and their addresses will be separated by just the leftmost bit they will have. So this will be like 0, 0, 0, and this will be 1, 0, 0. The other 2 bits indicate that they both belong to frame 0. That's what this bit specifies here. And so in this example, we actually have a block 0 in our frame 0. If now we all of a sudden have another address generated by our CPU, which shows 1, 0, 0. Never mind these 5 bits. I'll talk about this briefly in just a second. Then that means we have to bring this 1, 0, 0 block, if you like, into frame 0, 0, which is frame 0. And these 5 bits just simply tell us exactly which word it is in this block that is now in frame 0. So this block ID that we talk about, block tag, tells us which of the 2 blocks actually sits in frame 0. Same is true for block 1 and block 5, and their address patterns will be, just for this case, for example, 0, 0, 1, and for this it will be 1, 0, 1. Again, 0 and 1 on the left-hand side separate these blocks by their block tags within this frame, but 0, 1, that gets tagged onto the rest of the first 3 bits, which will be 0, 1 in this case as well as in this case, simply tell us that they must both go to frame 1. And the same happens with block 2 and block 3 and block 6 and block 7 respectively. 2 and 6 are together and 3 and 7 together. Now you could do other assignments here, but we just picked the simplest one where we kind of, in a way, shuffled these 4 blocks with these 4 blocks to generate our frame pattern here. So that's really the idea of a static mapping. And one other thing that has to be now discussed here is the replacement idea, the policy. How should we replace things? Because things have to be replaced once in a while. We could really have 2 different ways of doing this. One is called write through and the other one is called write back. Again, we just talked about this in class. And for this particular sort of direct memory or static assignment, I'm going to describe the write through method, and then we'll talk about write back later on. So here we have what's called the write through policy, and of course, whether it's write through or write back policy, we have to talk about reading and writing things. And so basically, write through means that every time you actually change something in the cache, which is certainly a block in a cache in one of the frames that we talked about, you're going to be making that same change in the main memory as well. So this block as an image, the block in the cache as an image in the main memory. So if you actually write into the block in the cache, you also write into the image of the block in the main memory. So you kind of keep it updated. And I told you in class that if in fact we have nothing but write instructions, something that constantly changes memory, then this makes no sense, because why would you then have a cache? Because every single time you're updating cache, you also have to update the memory. That means you created yourself a lot of work. So you have to assume that the writes are not very frequent. Now with that sort of stated, I also mentioned that this may give you some benefit, because it distributes these writes over different machine cycles, instruction execution cycles. So that way, when an instruction comes upon you where you have to replace a block, you don't actually have to save it back into memory all at once. So for example, when we're reading something and we don't really find it in our cache, which will be called a read miss, as we described it here, that would require us, in fact, if we hadn't used the write-through policy, that would require us to save this thing that we have in one of the frames in the cache, a block, so that we can bring the other block into that same frame, because they use the same frame, as we just saw. Like block 0 and block 4 use the same frame. So the idea is this then: to read, we determine the frame. The frame is basically picked out of the 2 bits after the leftmost bit in the example we did, and our block needs to be there if in fact we were to make any changes to it. So we then take the block tag of that block that is sitting in that frame, and then compare it to the block tag that is coming with the address that is generated by our CPU. If they agree, then we have the block in cache. Our block is in the cache. All we have to do, since we're reading, use the 5-bit word address from the remaining of the 8 bits we have, that is, in the first place, generated this request, the read, and then locate it in the block within that frame, and then to be done with the read process. If that's not the case, all we're reading, of course, in this case, what we're doing is to read, so nothing else needs to be done. If, on the other hand, block is not in the cache, and it can happen when we search for the tag, and that frame that we have to look in to see if our block is in there does not have the block tag that we came up with when we generated the address, then we have to replace the block in that frame, and that's called the read miss. And so that requires loading the desired block into that very frame. Once we do that, then we use the 5-bit address to go to our word in that block. So because we use the write-through policy here, we don't really have to replace. We don't have to rather save the replaced block. That's what I mean. And so because we've been doing the saving, gradually every time a write request has been generated by our computer, that we did already. Now that we're going to see in the next slide, that when we actually do the write, you will see that we're doing a write through. So because of that, there's no need to make any no need to save the replaced block. The block that we're replacing can be just basically overwritten. And that saves us now the time to take the entire block that we're replacing and put it back into memory. So that was what I was saying, that instead of like doing this, in one step where a whole block of words have to be replaced, and that will certainly create a huge latency on this particular sort of operation, the read operation. We do this gradually. Every time there's a write, then we just make the write in 2 steps. We save the word into the block, as well as we save it into the image of the block in the main memory. So now the write-through policy and the write instruction, something that actually writes into memory, happens with this write-through in mind. So we determine the frame. We compare the block tag of the frame with the tag in the address register, same way that we did with the read instruction. If they agree, we know that the block is in cache. So now we're going to write into the block, but we also have to write into the main memory. So we use the 5-bit address in the address register to locate and copy the word from the register into the frame. This register that I'm referring to is in fact coming out of here. the scratch pad. It could be one of these registers that actually wants to write into, or the instruction that we're executing, the write instruction, may want to write into one of these blocks that are sitting in the cache, or may not be in the cache, so we have to bring it in. But this is the case when we found it to be in the cache. So we got that in the cache, and we update the actual word in there because we're writing into the block. But that is not this one here. That's a read case. This is the right one. So we copy it from the word from the register into the frame, but we also have to take this now 8-bit address, the entire address, to copy the word into the main memory, into the image of the block that we are updating here in the actual frame that we found our block in. Now, it's also possible that we may not find the block in the cache. That's called the write miss. In this case, we're going to have to bring the block in, and this is when we also get to save this process of replacement, because we've been changing in this step here every time we find it in the block, in the cache rather. We've been updating not only the block but also the entire memory, or the image of the block. We first, this is a cache miss, a write miss, I'm sorry, and we load the desired block into the memory. Into the frame, I'm sorry. It's just a writing of the block from the memory into the cache. And we use the 5-bit address as before to write our register into the block. So we move the word from the register into the frame. But then we use the entire 8-bit address to copy the word into the main memory. Now the block that we replace, we don't have to worry about this, because in both of these cases, when we actually do a write, we also updated the image of the block. And the one that was there, we don't need to worry about it, because just like I said, in this process, which is the process where now we're dealing with the new block, as you can see that in both cases, whether it's actually block is in the cache or not in the cache, we are updating the image of the block in the main memory. So as I say over here, there's no need to save the replace block because we do this in a step-by-step fashion. So in both the write and the read execution of these two instructions, write and read instructions, there is no need to save the replace block. And again, this would also congest the computation of, or the execution of a write instruction if we were to sort of like not do this right through. What we need to keep in mind, of course, is that we don't want to have write-throughs. We don't want to have a lot of write instructions when we actually have write-through policy, because then it will just amount to creating additional overhead. Not only we have to write into the main memory, because, as we are doing it here, but we also write into the cache, so that's the extra time. And why even do that? We talked about this earlier. So this thing pays off if, in fact, writes are not too frequent, and that the advantage being is that because we spread it over time, we would not congest the system, as in fact these read instructions and then write instructions come up down the pipe for us to execute. Now, one problem we found out with this fixed mapping or static mapping was that the blocks were assigned only to a given frame, and that made it sort of not very advantageous, if you like, or effective when in fact a given block was used a lot more frequently than another block. And if we assume that all blocks are used as frequently, then one option would be to create what's called a fully associative cache, where each block can actually be in each frame. Now, the addressing mechanism for this will be somewhat, slightly more involved, because we no longer can look at the 2 bits, to say which frame that our block would be in, because our block could be in any frame. That means some search needs to be executed. But because we have 4 frames, we still may want to think in terms of this division that I talked about, where we have a 1 bit of a block tag and 2 bits of frame address. So when we use the same allocation, for example, if the rightmost 2 bits of the 3 leftmost bits are used for frame reference, then we just take a look at that frame for a given word and see if in fact the block tag that we are looking to identify our block with, which would come down the address pipe, to see if that is that's found in that frame. If it's not found in that frame, we go and search for the next place. So really, in this case, if you think about it for a second, that 2-bit address plays very little role because we are assuming that this block could be anywhere. Now, of course, the only thing that it would be used for is when we find our block in, or we don't find our block in any one of these and we want to bring it into it, then we just have to assume that when we assign this to frame 2, for example, that this block, let's say 0 goes into 2, we will make that association with block 0 and frame 2. So we will say that block 0 isn't actually frame 2. So in that regard, those 2 bits will be relevant only to the identification of the frame. Otherwise, whatever comes down from the address decoding mechanism on the CPU side will give us a 3-bit address portion there, only the block ID of which will be relevant. The other 2 bits just simply tell us where this particular block is in the main memory, but it could actually be in one of these 4 frames. That means we're kind of voiding those 2 bits because we can place them in one of these 4 places. So whether it's 00 or 01 or 1011, if a block can go into one of these places, that means it could actually, its frame ID could be anything. It could be 00, 01, 1011. So only to that extent we kind of use those 2 bits, not in the address register, but in the frame space, the cache space. Those 2 bits will be relevant. And some search will have to be needed, will have to be conducted in order to find out exactly which of these 4 frames that our block actually resides in, if in fact any one of them. We have 8 blocks, keep in mind, that we may still not be able to find a given block. Since we have 8 blocks and 4 frames, let's say that these 4 blocks are in the 4 frames, and then block 4 comes in, it's not there, so it has to go into one of these places. So the process is we first search to see if block 4 is in there, in one of these frames. If it isn't there, we then place it in there. And then the block tag that gets put in here basically tells us which block is in that frame. So we really don't pay attention to the frame ID or the sort of like the portion of the 3 bits, which would be the last 2 bits out of the leftmost 3 bits. Basically, those are not relevant to, because we're searching each and every frame to see if our block is here. It's only block ID that matters. All right, so that is fully associative cache, and it requires a lot of searching. Instead of doing that, we could also use what's called set associative memory, where we take our cache and then divide them into sets. In this example, we have 2 sets. Frame 0 and frame 1 constitute one such set. Frame 2 and frame 3 constitute the second set. And our scratch pad is still here, so we actually move things back and forth between the cache and the scratch pad before we go to the main memory. Now this is a irregular, I call, a set associative cache, because as you can see that this first block, for example, is assigned to all the frames. The next block is assigned to the first 2, and then the third block is only assigned to frame 2, and then the 4th block, which is block 3, is assigned to frame 3. And some other ones are assigned, like 1 or 2 and so on. So and these are written down here. So hopefully I haven't made any mistake in copying them down. Block 1 can be mapped to frames. Actually, this is not quite true, so I have to change that. I just noticed that for a second. So this is actually not quite right. This must be basically F2 and F3, and hopefully the other ones are right, but you can fix them. I just noticed that quickly. Okay. So let's just move this up. If it goes. My machine does this sometimes. Alright. So let me get back to the display mode again. That's actually 4 places it goes to. I guess you get to see that. Let me just move this. This is just a little odd here. Okay, and then I can move this a little closer this way. Okay. So that's the idea, that this is an irregular. You may wonder why would we would want something like this. The idea, of course, is as we talked about, some blocks may be required, may be more frequently used than other blocks. In this example, of course, block 0 is assumed to be such a block. And when that happens, you'd like to put that in there with all the frames. Again, when you make this kind of an allocation, you really this graph that you see here is some kind of a table which maps your blocks to your. So you could identify, think of a binary matrix of sort, where the blocks are maybe the rows and then the columns are the frames. Wherever there's a 1, you can say there is actually an identification of that block with that frame. So if block I, let's say, which will be row I, and then column J, which will be frame J, if there's a 1 in the matrix, you can say that this association exists with it. And so you can search for this. And then this binary matrix becomes a tool, if you like, a simple data structure through which you can actually determine which of these frames you should search. And you can see that the notion of the frame address that we used in the fixed mapping, the static mapping, kind of goes away. But it will actually come right back up again when we make this irregular pattern into a regular pattern, because we can now have some structure, in which case we could still think of these representations properly. So here's a regular design, and by that I mean, we get block 0 go to frame 0 and 1, block 1 go to frame. This is again another mistake that I just committed here. It should actually split between 0 and 1. So this is not a good diagram. I wonder if I could actually update this. I don't know how I ended up. It seems like some of the connections have moved out of their places. I don't know how this happened. Well, I really don't know how I ended up doing this. However, we can try to fix it. Maybe this kind of moved. There are a lot of connections in here that came in somehow. I don't know where they came from. I'm just going to have to delete those, because I don't see that they belong to anything here. Some extra connections were made, so I'll just delete those. Now this also seems to be somewhat excessive. So what I was saying, that I think this would actually have to be shifted. So if I could make a change, it seems like this is just an image. All right, so let me see if I can draw something over and beyond this. Let's see, maybe that's what happened. So I really want to show this like this. And this should be crossed out, this other one. Or if I could just do freehand here. Not sure if any of these is a freehand. But I just want to erase this. So I don't know if I could erase this. So that connection is just wrong, and I hope that I fix this. Let's see. Just assume that the red connection comes in instead of this connection, and I think everything else seems to be okay. For example, block 3 goes to frame 2 and 3, and then block 4 goes to 0 or 1, and then 5 goes into 2 and 3, 6 goes into 0, 1, 7 goes to 2 and 3. It's just that this is the one that's just like not right. And let's see if I can quickly. It is kind of hard to do this in Microsoft, but what I really wanted to do was, this is just a curve. There's no freehand. There probably is somewhere, but I can't find it right now. And yeah, I cannot draw over this. Just it's an image. It doesn't let me draw something on it. So what I'm saying is that I just can't do that. Yeah, there's no freehand here. So if I did have it, I would simply. One thing I can do, of course, is just pick this and then pick a color that is not going to. It's going to be just. All right. Yeah, I have to pick a color for myself. All right, never mind that. Just assume that the red one replaces this black one here. So this is not there, but this one is there. All right. then everything else works. So this is more as we looked at this in class. You recall this. This pattern is fairly straightforward. You can see how this actually works out. That this block 0, for example, goes to these two frames, and that means that we really have to think about this as basically having set 0 identified with it, and this block 1, now that we remove this and put this in, going into set 1, and block 2 going to set 0, block 3 going to set 1. So the way we think about this is, it's like block 0 goes to the even indexed set 0 that is, and we consider 0 to be an even number, and block 1 goes to an odd one, that is set y, set 1. Block 2 goes to an even set, which is set 0. Block 3 goes to odd. So in other words, it is the rightmost bit of these 3-bit address patterns that come out of our blocks that determine which of these sets we go into. Within the set, we could actually find our block either in frame 0 or in frame 1 here, or in frame 2 or frame 3, depending upon whether in fact our block gets mapped to set 0 or set 1. So effectively what I'm saying is that we have a 1-bit set address and then 2-bit block tag. And if the set address is 0, as in the case of, for example, block 0, we're going to be in set 0. If it's 001, that means our block has a 3-bit ID of the ID of the block, in this case, is 001. And then we use that rightmost bit to identify which set out of the 2 it goes into, and then the other 2 bits would tell us which of the if our block is really contained in this particular. Now you again notice that 4 blocks get mapped to each set. So this set 0 receives block 0, block 2, block 4, block 6, and then set 1 receives block 1, block 3, block 5, and block 7. So it's possible to be blocked away or to be blocked out of a set because got 2 frames and then 4 things coming in. So you may be prohibited from coming in, and so you still have to have some replacement policy in place. But this time we've actually increased the amount of or the probability of a block finding a frame inside a set, because now block 0 goes to both frames, can go to either one of the 2 frames. Block 1 can go to either one of these 2 frames, and so we kind of increase its chance to find an available block. That didn't completely avoid a block from being block having the ability to access a given frame, because they could both be occupied, as I said. So this is really the idea of a set associative cache. Now, and the rest of it works the same way. The only difference between this and the very first fixed static map that we had was we really had a 1-bit block tag, and then we had 4 sets. When the number of sets coincides with the number of frames, we don't have set associativity anymore, because each set contains only 1 frame, and we degenerate back to the so-called static mapping. This set associativity makes only, even though it's a special case, I should also mention that. That is, if in fact each set consists of a single frame, that is the set associative, but it's sort of not very practical, because each frame, each block gets assigned to only 1 frame in this case. So the very first example we did, which we call the fixed or static mapping, is set associativity with each set degenerating to a single frame. In this case, each set holds 2 frames, and this is a proper set associativity where where each set gets to have 2 frames, and therefore there's an ability on the side of the block to go to one of the 2 frames. And in the address mechanism here, it translates into a 1-bit of set address, which was actually a frame address, which was, in our example, was 2 bits, and now 2-bit of block tag. So we had a 1-bit block tag in the example we did. Now we have 2 block tag bits, block 2 bits block tags, and then we have a 1-bit set address instead of like having 2-bit frame address. And this set tells us that tells us which frames that this particular block is able to go to. So this will be set 0, inside of which we have 2 frames. And then in set 1 has 2 frames as well. And so we could still map the addresses properly from the memory address into the frame representation. But because we have the capability to move our block, let's say 0 into frame 0 or frame 1, this sort of tag that we have has only limited implication. This is just the tag of the frame, the block, but it can be found either in frame 0 or frame 1. So we kind of only pay attention to the remaining bit, which is our bit address. And so this, unlike in the direct mapping case, there's no one-to-one correspondence between the pattern here and the pattern that kind of represents, if you like, our block in one of these 2 sets. Now, block 0 could be in frame 0 or in frame 1. So basically what we're saying is that our block 0 is either associated with 000 address or 001 address, if you like. That's how you'd like to think about this. I mean, frame-wise, this is how these frames are, basically. Or I should say, actually, 0, 0, which will be frame 0. And yes, the frame 1 would be 001, but that's not, how these 3 bits represent things. We only use this set address, this bit for the set address, to actually separate things into these different categories, different blocks. Set 0 is used for block 0, block 2, and then block 4 and block 6. That's how they come in. And then set 1 is used for block 1, block 3, block 5, block 7. So it may actually be even best not to make this identification too explicit in terms of what it really means to have 000 in the address register, if you like, as it relates to the mapping here. The only thing that you have to pay attention to is that just look at the set tag, and if it's 0, you know that you're in the upper set. If it's 1, you're in the lower. And don't give any more significance to the remaining bits, because that's going to be used only as a tag to find this particular block, let's say 0, either in frame 0 or in frame 1. And we know that it's a fixed address for block 0, it's 000, but it could actually be found in frame 0 or frame 1. It seems like the address is kind of like implicitly changing because it could be in 1 or 2 places. That means your address must change, but it doesn't, because we have to sort of like search by the tag of the block to see where it belongs. Not so much by the address that we see, 000. We just take the 00 portion of it and then search inside the set. Okay. I think I've said enough about that. And now the only other thing that actually we need to look at is the replacement policy. In this case, we could use what's called write back as opposed to write through. And this policy is just, I'm talking about this here just to give you the other example. Either one of these policies can be used with set associative or fixed memory mapping. But in this case, we're going to look at write back policy. So here's a write back policy. We're doing, again, read and write. When we're doing a read, we search the block in the frame set. This is to read something from it. If it's found in the set, it's in the cache. And so this is, since it's a read, we don't really have to do anything except to read what we're supposed to read. We use the 5-bit word address, which is outside of the 3 bits we talked about, in the address register, which is basically these 5 bits here, to locate and move the word from the frame into the register. That's what we do. And nothing else has to be done. Now, when we're doing a read and we don't find it in the cache, the block, that's called the read miss. Now, this is the time where we actually have to kind of write things back into the main memory. So this replace one of the blocks in the frame set with the block that is needed really means that swap them. Let me just actually just make that change so that this significance of that. Oops, must have had this in not a text mode, but let's see if I can use it. Okay, let's see if it works. Yeah. So maybe swap. Now, when I say swap, of course, you don't really take physically these things and swap them, but you take the one in the memory into the cache, and then the one in the cache into the memory, into their respective locations, of course. You're not really replacing you're not using the original locations in the memory. It's not like they coincide. They're in different places in the memory, so they go back. The one that's being kicked out of the cache, it goes back into its own space. But I call this swap because we're swapping out of the cache. And the swap says, when you replace, replace sort of sounds more destructive than swap. So swapping means like you take the thing out, and that's where the write back policy comes in. It's not write through, but it's write back. We're actually writing back what might have been changed. Now, one of the things, of course, because this is a read instruction here, one thing actually we could have done here, which I didn't seem to have paid attention to, is when we make this swapping, we could have had two situations. One of which would be, and I think I showed this in the write command, and this also has to be done here. I just realized that we have a possibility of having what's called a clean block and a dirty block. If in fact within our set we happen to have a block that is not changed in terms of like being written, then we can just replace. And let me see if I could just write this. Okay. And maybe I could just do this. If it is possible, use a clean block on the swapping. Now, if it's a clean block, this can be replaced. Okay. Otherwise, swap a dirty block. Now, that's called a dirty block. It's just a technical term that's used with the block to be cached in. The word swap then I think is only relevant when we're just like swapping a dirty block with the block that we want to cache in. But I just made this swap instead of replace. Maybe I could even fix this. Okay. Let's see if this actually makes sense. Replacement. Otherwise, swap. Maybe that's when the swap comes in. Okay. So that's how you do it in the read, because again, as you're reading, since you're replacing a block, it's possible that the block that you're replacing might have actually been written into in a prior instruction or two. So let's go back to the slide presentation mode. Now in the next case, we are still using the write back policy, and now we're going to have to do the same thing on the right side. So if the block is in the cache, then we use the 5-bit word address in the address register to locate and copy the word from the register into the frame. And that's all we do, because we're not doing write through but write back. We found the thing in the cache, and we will actually do this saving of the block as a write back, not as a write through. So it's not done instruction by instruction. And in this case, nothing else is done. If you remember, in the case of write through, we would still have to write the word that we're writing into the block, into the image of the block in the earlier algorithm. Else, which is the critical part, if block is not in the cache, which is a write miss, check to see if a block is clean. If there's a clean block is what I really meant to say here. It's kind of a little bit ambiguous. There is a clean block. Clean meaning like it hasn't been updated. A clean block. If so, replace the block that we have we want to write into with the one that is just clean, that has not been changed. Else, use a replacement algorithm, or a replacement algorithm, I could say, to select a block for replacement and swap that block with the block that is needed. This is what we did in the earlier step as well. And then use the 5-bit word address in the address register to locate and copy the word from the register into the frame. So for a block to be clean, just keep in mind that it should have been a block that we brought into the cache only to read from it, not to write back into it. So it has to be that kind of a block that we can really replace this new block that we want to write into this time. But that block, whether it's actually we're writing or reading, has to be a block that has only been read from, not written into, and that's kind of critical. All right, I think this is probably fairly clear. Now, what I want to talk about briefly here is switch gears and then, discuss replacement policies, exactly what kind of replacement we use. Some more examples will be done in recitation classes. Chua Lin would conduct some examples of these, and just do some examples in the recitation classes. So we could have several different ways to replace blocks. One would be least recently used. One may be most recently used. Even though this is not very practical, it may be done only in the name of fairness. If something is used all the time, or most recently, maybe you want to take it out of there. Last in, first out could be one that could be also not as frequently used, because if the one just came in for a possible read or write instruction, then why would you take that out? Maybe it would be used again. And then, but last in, first out doesn't necessarily mean that that you didn't end up basically having some separation of accesses time-wise along the way. You could have, last in maybe separated by one that's used more frequently, and so that doesn't necessarily mean that the time of usage within the memory, the cache itself, coincides with the timing of the arrival. And the first in, first out is something that is maybe more reasonable. And then finally, the optimal scheme, where you actually look as far as you can to see if a block would not be used for the longest number of machine cycles, and then kick that out of the cache. So here's a couple of examples. Now we have a page trace. This is called a page trace here, which means that you got some 6 pages from the numbers you can surmise, 6, 1, 4, 6, 2, and so on. And then you have 2 different algorithms displayed side by side, one below the or above the other. So least recently used means just that. The one that is used least recently is the one that's going to go on. And then in the last row here, we indicate the faults. So, and then we compute what's called the hit ratio. How many times we actually found what we're looking for in the cache. So 6 initially is not in our cache, so it comes in, there's a fault. 1 comes in, it's a fault. 4 comes in, it's a fault because it wasn't there. And now 6 is requested again, it is in there, so there's no fault. 2 is going to come in, and we look back to see exactly which is the one that is least recently used. Now in this case, it's actually when 2 wants to come in, we want to see the one that's least recently used. Clearly 6 isn't the one. 4 isn't the one, but 1 is. So 1 must go. And in this case, 1 gets replaced. 1 replaces 1. 2 replaces 1. 2 is the one that wants to come in, and 1 gets replaced by 2. Now 3 comes in. 3 is not in our 6, 2, 4. By the way, this was a fault. Now 3 wants to come in, and we look back to see which one was used least recently. Not 2, not 6, but 4. And so 4 goes out, 3 comes in. And now 4 wants to come back in. 3 is not the one that's least recently used. 2 is not the one that's least recently used, but 6 is. So 6 actually goes away. And then, you kind of keep doing this. The 5 now wants to come in. This was a fault as well. 4, 2, 3 are in the memory. So 4 is not the one that came in most recently, least recently. 3 is not the one that came in least recently. It is 2. So 5 actually replaces 2 in this case. So you kind of continue along the way, every time marking which one is actually going to generate a fault, which one won't. So we count the blank cells, 1, 2, 3, 4, 5, 6, 7, 8. So the hit ratio is 8 out of 20 requests. First and first out is what comes in first goes out first. So again, 6 is a fault because it was not there in the first place. And 6 and 1 comes in, it's a fault. 4 comes in, it's a fault. So we now have 6, 1, 4, no fault here, as it wasn't a fault here. 2 wants to come in, and we actually look back over here to see which one had come in first. It was 6 that had come in first. So 6 must actually go, and then instead of 6, we have to put 2 in. So this is where things differ a little bit. Here we didn't replace 6 because 6 was recently used, and we replaced 1 in this case. But here we replaced 6. So because it was the first in, we look at the time it arrived, not how recently it was used. So you kind of go along the same way, and you generate this pattern of faults, and the hit ratio gets to be 10. So in this case, FIFO kind of works, it seems like, more advantageously. Gives you a higher hit ratio than this. If in fact, if I did all the paging or the caching steps accurately. So check this out to see if there's any mistake. If there is, you can always revise these numbers, but the point is, the idea is clear that the 6 had to be replaced here because 6 is the one that came in first. After this, let's take a look at this example. Now we have 2, 1, 4, and 3 wants to come in, and we look back to see exactly among 2, 1, and 4, which had actually come first, and that would be 1. So in this case, 1 is replaced. As you can see, that's what happened. So that kind of goes along the same way. Now finally, let's take a look at an optimal algorithm. In the optimal algorithm, we don't look back, we look forward. So 6 is a fault. 6, 1, 1 is a fault. So the first 3 would always be a fault because they're not in the cache. So we got those things in. Now, at this point in time, we were looking to replace something, but 6 is actually already in the cache, so we don't replace anything, so it's not a fault. That was the case in these other 2 patterns as well, or the policies. So that's not a problem. So now 2 wants to come in, and instead of going back and looking this way, we kind of look this way. As we look as far as we can, and then we could actually specify a window for this, but we're going to look for the rest of it. What we see here is that 3 is going to be used, even though 3 is not there. We have to be looking at 6, 1, and 4. So we look as far as we can. We see 1 being used sometime here, sometime later, and 4 being used as well sometime here. In fact, 4 gets used even closer to where we are now. So that means 6 is the one that has to be kicked out, and it is. That was a fault. Now 3 must be used. And we're again looking to see exactly which of these 3 blocks we want to replace. Looking down this way, we see that 4 is going to be used, so we don't kick it out. And then we see 2 is going to be used some time later. And 1 is the one that would not be used for the longest. So 1 must now be replaced. And that's what we do here. 1 gets out and 3 goes in. And now we have 4. There's no fault in there, so we stay with 4. And now that we've done that, we look to see what we do with 5. 5 is going to be replacing the block that's not going to be used for the longest. 2, certainly not that one. 3 is not that one, so it must be 4. So 4 goes away. That was a fault. From this point on, we have 2, which is in the memory, no fault. 3 in our cache, no fault. 2 in our cache, no fault. 5 in our cache, no fault. 5 in our cache, no fault. Now 4 wants to come in, and we look further down this way to see exactly which one must go. So we see that 2 is going to be used, and so would 3. So 5 must go at this point in time. Here. And then 5 goes away. Okay, and that means we have a fault. And then 4 is the one that we want to use, no fault. 2 is the one that we want to use, no fault. 3 is the one that we want to use, no fault. And then 1 is going to generate a fault. At this point in time, we see nothing but 2, so we could actually replace either 3 or 4. I elected to replace 3. And in that case, 3 goes out and 1 comes in. And of course, the next 2 are blocks 2 requested, no faults here. So when you add these numbers up, 3, 5, 6, 7, 8, that means 12 over 20. So that's the highest hit rate among the 3 we picked. And of course, this is an optimal algorithm. Now, there is an anomaly that's called Bilatti's anomaly. And this anomaly it points to something. And the algorithms that actually do not cause this anomaly are called stack algorithms. Now, FIFO is not a stack algorithm. And Bilatti actually proved this. And the idea of a Bilatti's anomaly is that when you increase the cache size, the number of faults increases as well. So you can see this in this diagram. Now here we have a FIFO with 3 frames, 1, 2, 3, and so we bring these things in. 1 comes in, 2 comes in, 3 comes in, each of them generating a fault. 4 comes in with a fault because it's not there. And then 1 comes in, 1 is not there, so it's going to be a fault. 2 comes in, it's going to be a fault because it's not there. And then 5 comes in, it's going to be a fault. Now 5 is there, no fault. 5 is there, no fault. Then 3 comes in, it's a fault. Then 4 comes in, it's a fault. And then no fault. So now if you count the number of times that we didn't really have a problem, it's 1, 2, 3. So the hit ratio is 3 out of 12. Now when we increase the number of frames from 3 to 4, that means 1, 2, 3, 4 frames, this is what we experience. We get 1 fault, 2 fault, 3 fault, and 4 faults already built up. Now 4 comes in, there's a fault. 4 comes in, I'm sorry, 4 comes in, there's no fault. What am I saying? Because we have 4 frames. So 4 comes in, no fault. 4 comes in, no fault. The first time it comes in, there's a fault because we didn't have it there. But now that 4 comes in, no fault because we had it already. And then another, my computer's really acting up here. Another 4 comes in, no fault. But then 5 comes in. This is the interesting sequence here. When 5 comes in, we take 1 out of there because that was the first one that came in. Now to replace, we replace 1 by 5. So 1 disappears, 5 goes in. And then 1 wants to come in, but that's a fault. But then 2 goes in, out. Now 2 wants to come out, and 2 we just kicked out. 2 wants to come out, and we take out 3 for that. Now we have 1, 5, 4, and then 3 wants to come out, the one we just kicked out. Now you can see that this sequence is written in such a way that the one we kick out is the one that we demand in the next clock cycle or the machine cycle. And so that's what generates all these faults. When it does, the hit ratio becomes 1 and 2 out of 12. So this is the point that Bilatti made, saying that if I actually use more frames, I may end up having a smaller hit ratio or a larger miss ratio, which would be like 10 out of 12. In this case, it would be 9 out of 12. So that's the whole idea of Bilatti's anomaly. And I think with that, I come to the end of this video lecture. And so all I have to say is we're going to cover pipelining next week. Until then, happy Thanksgiving, I should have said. Let's just fix that. And I hope that you all enjoy your break until Monday. So we'll see you Monday at 12:30 in our regular classroom. Take it easy.